Welcome everyone to our presentation, Black Hole Hunters. This was a citizen science research project that we worked on as a part of the NASA SEAS internship.
Hi, my name is Miranda Blell, and I'm a rising senior at the North Carolina School of Science and Mathematics. I hope to attain a bachelor's degree in both geology and astrophysics with the goal of eventually conducting research with NASA in Antarctica.
Hi, my name is Isabella Levine, and I'm a rising senior at Sleepy Hollow High School in New York. I hope to pursue a career in aerospace engineering and mathematics with the goal of becoming an astronaut one day.
Hi, my name is Nicole Deng, and I'm a rising junior at Oakland High School from Northern Virginia. In the future, I plan on pursuing computer science and astrophysics, as well as studying their intersection.
Good afternoon, everyone. My name is Natalie Hoeschle, and I am a homeschooler from Brenham, Texas. After 12th grade next year, I hope to study astronomy in college, and my ultimate dream is to become an astronaut.
It is important to establish the background which we based our research on. The goal of the Citizen Science Project is to manually sift through brightness measurements from Zooin versus SUPERWASP black hole hunters to determine the presence of black holes, which computers cannot decipher. So by doing this, we would essentially be serving as citizen science, which refers to a member of the public who volunteers to partake in scientific research. However, we decided that we can learn more from data provided than just identifying black holes, and we wanted to make our own inferences from the SUPERWASP data we were analyzing. So SUPERWASP, or the Wide Angle Search for Planets, is a multinational consortium of multiple academic organizations. It is financially supported and operated by Warwick and Kiel universities in the United Kingdom. It consists of 2 robotic observatories that run throughout the year, one in each hemisphere, being Spain and South Africa, which ensures that the data collection is continuous throughout the year and the seasons. So it uses transit photometry to hunt for exoplanets. However, this can also be used to find black holes, especially stellar black holes, as well as variable stars. So some of the data may, however, be unreliable due to noise. As each pixel is being read out by the computer, a few additional electrons are being lost or acquired randomly, causing the readout value to deviate a bit from the actual collected signal rate, which creates unreadable data when the object is especially faint. So there are 2 primary compact objects, black holes and neutron stars. Although in this presentation, all compact objects we will be referring to, however, will be in reference to black holes. Black holes are extremely massive and dense celestial bodies, and they are formed when a massive star collapses onto itself. And by massive, we mean greater than 8 solar masses because of its immense gravity. So most stars exist in binary or triple systems. So if one star dies, the 2 entities will continue to orbit each other until the gravity draws them in closer and closer to one another. So the separation distance gradually decreases over the course of millions of years. Subsequently, the black hole accretes its neighbor's matter. And these systems in this phase are especially hard to find because they occur for a relatively brief period of the system's lives, although, as I stated earlier, they can be up to millions of years. Additionally, these stellar black holes we are looking for do not emit X-rays, as the components are extremely far apart, making them findable only through alternative methods, such as lensing, which we will get into. Why do we use lensing techniques? These special binary systems make it possible to detect black holes because of this phenomenon called self-lensing. Self-lensing occurs when an orbiting black hole transits or passes in front of its companion star. So because of this, the black hole, as I said, is incredibly dense and heavy. So the bending of space-time due to the gravity around the black hole essentially acts as a lens which magnifies the light of the star behind it, making it appear extremely bright, as you can see in this graph in front of you. So the light curves show to be symmetric, a peak in the otherwise stable brightness of the star. Although astronomers believe that there are numerous black holes within the Milky Way galaxy, observing a self-lensing event like this is extremely rare because these transits occur once every few decades. This is the anatomy of a light curve. The graph presented here is an eclipsing binary light curve, and as you can imagine, this is very similar to some of the readable light curves we observed in Zooin versus Platform, where the x-axis is listed in the number of days, while the y-axis displays brightness or magnitude. From here, we use properties of a graph, such as the period, differences in maximums and minimum magnitudes, and a shape to make inferences about the celestial bodies that we were dealing with. So amid the thousands of pieces of data we looked through, we noticed that some graphs displayed repeated patterns which were not classifiable as black holes. After beginning to catalog some of these graphs out of curiosity, we realized that they were in fact akin to the distinctive light curves emitted by variable stars. As you can see here are some of the types of variable stars that we cross-compared with our graphs, including intrinsic stars such as rotational variables and eclipsing binaries, as well as intrinsic stars such as RR Lyrae, Cepheids, LPV, and Delta Scuti.
This is our methodology. To begin analyzing the citizen science data, the team underwent training to learn what characteristics the light curve of a black hole candidate would have. After training, we sorted through both simulated and real data, racking up a total of 6,710 total light curves by the end of the analysis. While looking through the data, the team looked out for both black hole candidates along with graphs that resemble variable star light curves. By looking for both, we were able to contribute to a variable star research by classifying as many different objects as we could. Then, from each real light curve that resembled either a black hole candidate or a variable star, we extracted the subject ID, right ascension, and declination and input them into a Google Sheet. After inputting the data into a Google Sheet, each light curve was classified into its most probable type as a variable star. The options that were decided on were black hole candidates, eclipsing binaries, rotating stars, RR Lyrae, Cepheids, and flares. However, we found no RR Lyrae stars. RR Lyrae stars and Cepheids are types of pulsating stars. Our primary goal was to look for black hole candidates, one of which is shown in this picture. A black hole candidate is set apart by an obvious sharp and symmetrical peak in the graph. One type of variable star classified was the eclipsing binary. Eclipsing binary graphs typically have rounded tops and sharper valleys in between, and periods less than 3 days. The next is a rotational variable star, which was the most populous in the data. Rotational variable stars have small amplitudes, symmetric up and downs, periods up to 100 days, and typically a lot of noise. The next light curve depicts a Cepheid, which has periods up to 80 days, larger amplitudes in rotational stars, and a steep ascending branch followed by a shallower descending branch, or vice versa. It is less symmetrical from the others, which sets it apart. Long-period variable stars are similar to rotating stars, but have much larger amplitudes and periods ranging from 80 to 1,000 days. They appear sinusoidal and are symmetrical. Flares were identified by light curves with more than one peak. They resemble black hole candidates, but have multiple peaks with different heights, which repeat more or less evenly spaced. As I previously mentioned, we looked for but never identified RR Lyrae. RR Lyrae light curves resemble the shape of a Cepheid light curve, except they have a period of only a day or less. After each of the 400 objects were identified as some kind of variable, they were classified again by a different person without seeing the first classification to avoid bias. If the classifications matched, that became our official designation of the graph. If the classifications did not match, the group discussed the light curve together and consulted our mentor to verify our final decision. After classifying each star, we checked the SIMBAD astronomical database to see whether any of the stars were already classified, and which stars we had classified for the first time. Even if the stars had been classified in SIMBAD, their classification was often broad, such as variable star or high proper motion star, which allowed an opportunity for us to classify it further.
Now I'll explain our research findings. Over the course of the 2-week on-site internship, our team conducted 6,710 citizen science classifications through the Black Hole Hunters project on Zooniverse. We identified that 358, which amounts to 5.5% of our total, were pulsating variable stars that have not yet been identified or classified as such. As of 2022, there have been approximately 150,000 of these classifications completed. In total, our team contributed to 0.25% of all pulsating variable star classifications. First, I'll present our broadest classification, intrinsic versus extrinsic variable stars. Out of the 358 new classifications, the majority, 89.1%, are extrinsic variable stars, while 10.9% are classified as intrinsic variable stars. For our more specific classifications, we observed that 81.56% are rotational variables, 8.38% are Cepheid types, 7.26% are eclipsing binary stars, 2.51% are long period variables, and 0.28% are flares. As seen by the graphs and statistics, the most common type of pulsating variable star that we found were rotational variable stars. Now we'll take a look at the star type breakdowns from the SIMBAD database. Within the 358 identifications, 66.9% are labeled as unclassified stars. 22.2% are high proper motion stars. 4.3% are decided as double or multiple stars. 1.6% are RS Canum Venaticorum variable stars, 1.4% are variable stars, an additional 3.5% are less commonly labeled stars, such as irregular variable star or post-AGB stars. Through this, we can see that the majority of the stars we investigated are completely unclassified. Additionally, we also identified 11 potential black hole candidates. This is one example. Here, you can see a stable and consistent path of points leading up to an abrupt peak, showing potential for a black hole. This is another example. Similarly, there is a clear peak that stands out among the data points. Overall, 0.16% of our citizen science classifications are black hole candidates.
In conclusion, we met the goal for our project because we successfully identified black hole candidates, logged newly classified variables, and grouped them into their specific classifications by using light curves observed by SUPERWASP. To summarize our results, we sorted through 6,710 observations on the SUPERWASP database and identified 358 of them as new variable stars. Within these classifications, which comprised 5.5% of all our data, we calculated that 7.25% are eclipsing binaries, 8.38% are Cepheids, 81.56% are rotational variables, 2.51% are long period variables, and 0.28% are flaring stars. In all, we helped to classify approximately 0.25% of all the currently known variable stars. Furthermore, based on the number of black hole candidates that we found, we calculated that the approximate probability of finding a black hole through Zooniverse is 0.16%. Overall, through our research, we were able to extend this project beyond just black holes to also considering the existence of pulsating variable stars and classifying them into their respective types. Despite all of the successes of our research, like anyone, we had to work around limitations to our project and the inherent errors within. A possible source of error arose from the fact that the y-axis scales in the SUPERWASP graphs are in brightness, but the reference graphs we used for classification are in magnitude. This difference in units caused problems for us because a variable's amplitude is one of its defining characteristics. If the difference between these units is great enough, potential differences between the graph shapes could have misled us to classify some stars incorrectly. Finally, the domains of the x-axis limited the amount of data for each of the curves that we could observe, so we may have been missing the full picture for some of the graphs. This means that we might have classified some variables incorrectly because we couldn't see the whole pattern of the data. Because our time at SEAS was limited, we were not able to complete everything that we originally planned, but going forward, there are several possibilities to improve our results and further our research. One way in which we could do this would be to expand our data set size to increase the accuracy of our classifications. Another improvement we have already started pursuing is to check our classifications with professionals. And finally, one interesting twist to our project could be to calculate the lifespans and masses of our stars in order to predict whether they are currently black holes. All of the light from objects that reach Earth took time to travel through space. So the farther a star is from us, the farther in the past we are actually observing it.
SEAS was one of the most enlightening experiences of my life. Prior to enrolling in this program, I knew that I wanted to work at NASA. Although I had been under the impression that much of what they did was limited to astrophysics. Visiting Johnson Space Center, however, taught me otherwise. It enabled me to see the variety of people that were, quote unquote, working behind the scenes. And these people are actively contributing to the study of space. So it essentially allowed me to explore a field that I had never even thought about before, which was geology. I had always enjoyed traveling, so learning that analog expeditions were popular in this type of research and would simultaneously allow me to conduct research with tangible objects that I can physically work with really struck me. So personally, I believe that this is one of the most impactful experiences of my internship. It really helped me solidify the vocational path I really want to pursue in future. Pursuing that alongside astrophysics is something that I'm really excited to do. In addition, being able to work with my ambitious peers proved to be an invaluable experience for me, as it allowed me to meet like-minded people and develop my teamwork skills. Through working in the field, I got to learn more about topics like aerospace engineering, physics, and mathematics in ways which were relevant to my research, thus allowing me to grasp onto the information and learn how to apply it in an appropriate setting.
This was actually my second summer in Cs. Since I was virtual last year, I was given the opportunity to apply again this year to be on site. I'm so glad I was selected to come on site so I can experience what Cs was like in person and work closer with my group. It was a completely different experience, one that allowed me to become much closer to my teammates, listen to speaker series surrounded by other people, and participate in hands-on STEM activities. The biggest difference for me this year was visiting the Johnson Space Center, especially surrounded by people that share the same interests as me, because we got to explore and became so much more invested in what we were already interested in and hoping to pursue. Due to my time in Cs, I became sure that I wanted a career working in STEM and one that allowed me to work with teams. I'm extremely grateful for the opportunities NASA C has offered me over the past 2 years and the people it has introduced me to.
Cs is one of the most unique experiences I've been through. It was a great mix of engaging STEM activities, in-depth research, and group connection. This program has allowed me to grow in many different ways. As a student, I've been able to broaden my experience with astronomy, and Cs has inspired me to continue pursuing a career in the field. As simply an individual, Cs has allowed me to connect with a group of like-minded people who have made this program extremely rewarding and memorable. It has also challenged me to go outside of my comfort zone and get a sense of how it will feel to work in the real world and become independent after graduating high school. My favorite part about Cs was being around my extremely goal-driven peers and mentors, as seeing them work hard motivates me to become even more focused on my own aspirations. I'm extremely grateful for the Cs experience and would love to participate in similar programs in the future.
When I look back over the past 2 weeks, I still can't believe that I was blessed with this opportunity to engage in the Cs internship because it all seemed too good to be true. This experience greatly exceeded my expectations, and I enjoyed all of the team building activities, the various field trips, and the amazing research opportunities. I was also thrilled to get a taste of college astronomy through this project, and it inspired me to continue pursuing a lifetime of learning more about the beauty, order, and truth in the universe. Overall, I am very appreciative to all of my teammates for all of their great ideas, hard work, and effective collaboration that made this project a success. And I am forever grateful for my amazing experiences and new friends. To conclude, we would like to thank NASA, Cs, the Texas Space Grant Consortium, the Center for Space Research, and Zooniverse for making this amazing opportunity possible. Also, we want to thank Mrs. Baggio and Ms. Miller, who both put forth so much effort into this internship over the past several months. Last, but certainly not least, we would love to thank our mentor, Dr. Ries, for dedicating her time, thought, and effort toward assisting us with our project to help make it a success. Finally, here is a list of the sources we used for our project.
Thank you for listening.